it is well, wow, what an honor to hear Suki before me. It's like, that's amazing. And Chris, that's just fantastic. So I realize that I'm in one of a member of a very small club, I think, in that I was a GFDL employee when Chris arrived, and still a GFDL employee when Chris left. So that's been quite a career, and I'm just so grateful to have been able to interact with Chris and learned so much from him over the years, and he has just been just a cornerstone of all sorts of land efforts at GFDL. I think our model building, we really have 4 components, and land is one of those. And so he's been the linchpin, the leader on a quarter of your system model we do. Now, that's the modeling side, of course, so many major scientific accomplishments. It's just been immensely beneficial for many of us, especially myself, to have had Chris there for these many years and through these many organizations of GFDL, et cetera. So it's just been great. So I wanted to first provide 3 sort of quick ways of looking at the span of Chris's career. One of them is a little quirky, so bear with me there. And then talk about a little bit more depth one of the papers. So John, if you could click the first slide, please, click the button. So this is the era when Chris arrived, which I wasn't able to pin down the year. I heard 1988 earlier, I was guessing 1990, so it's somewhere in there. So, and Randy showed a slide like this. This was our state-of-the-art model at the era, the GFDL R15 model, and also known very affectionately as the Mojave climate model, because this is just such a pioneering development in climate modeling science. It's incredibly coarse by our standards today, 4 degrees by 7 degrees atmosphere in a 4-degree ocean. Doesn't have all the bells and whistles and lots of extra things that are in models now, but this was such a powerful tool for fundamental understanding, to derive new insights, and Chris fit right into that paradigm of looking at fundamental aspects of the climate system that stand the test of time. His papers continue to be cited today, and looking at fundamental characteristics of the land surface. And he was, of course, starting from a highly useful bucket model. He developed a whole series of land models that Randy just showed that sequence, all the way to L11.4, and he just really using fundamental understanding for important research findings. So John, if you could click on the next slide. I wanted to show the span of time as we've gone from sort of Chris's entry to Chris's exit. And the bottom panel is the top panel is showing simulated precipitation in this old R15 model. And you can see it. Actually, it's really quite powerful. It still gets the major precipitation system. This is from the Northern Hemisphere winter season. You can see movements of the ITC, et cetera. The bottom panel is from our latest model with the 25-kilometer horizontal resolution. So the model on top, horizontal resolution, is something like 500 kilometers on a side. The model on the bottom is 25 kilometers at a side. So it's a whole lot of grid points in the bottom panel versus the top panel. And you could see a lot of refinement. You see a lot of topographic features, et cetera. But all the fundamental features are there. And that's what Chris's work has really pioneered, of looking at the fundamental aspects of the climate system, maybe not getting distracted by so many extraneous details, but looking at the really fundamental aspects. And that's been a really fun characteristic. So this is sort of the first cut of looking at the span of modeling space that has occurred during Chris's time. Now, next comes a kind of quirky way of looking at things. So John, if you could press the next slide. This is the CO2 level in the atmosphere. Bottom is pre-industrial, 280 part per million. The top is present at 419 part per million. And by my calculation, so Chris's arrival at GFDL was right around 350 to 350 parts per million. So it's kind of humbling to think for all of us to think about how much CO2 has gone up during the span of our careers. That number is larger for me since I arrived there a few years before GFDL. But I'd also like to say how important actually it is for Chris to arrive at a place like GFDL. As we see the CO2 levels increasing, we see the climate impacts growing. Having someone like Chris sort of arrive on the scene in this era of rapidly growing CO2 and really addressing fundamental problems that are so important for society, how rivers change, how evaporation change, stresses on the system. This is really key. So Chris walking into our 350 part per million CO2 era and pushing and working so hard over the years as the world faces these ever-increasing challenges. So that's been a really important aspect in terms of Chris' work and how much it contributes to society. And so John, if you could press the slide again, next button, please. So another way to look at Chris's career is through the unbelievable body of his publications, really tremendous aspects. I think earlier the top 3 papers were cited, but I have here the top 9 papers, highly cited papers, and they're so powerful. You look at these citation numbers: 4,674, 2,529. those are some numbers that very few scientists see in their careers, and so they're really quite amazing. So John, if you could hit the next slide, please. So the top three, as was mentioned earlier, are all lead authored by Chris. They're all just incredibly important scientific papers. And then we fill out the rest of these top most cited papers, and 5 of the top most cited papers involve GFDL model development. And that's been so critical and so helpful for us. It's the science is superb, but also the integration of that superb scientific understanding into our model development process has been great. And these high citation numbers are from papers 15 years ago, 10 years ago, CM2, ESM2, AM3, et cetera. But more recently, the papers aren't on the citation list because they're younger, but Chris has also been key for CM4, SPEAR, ESM4. So our whole host of modeling history for the past 30 or 35 years has been really, Chris has been at the cornerstone, the foundation of that. So we're so grateful to have had him participate in so much of that activity. So John, if you could go to the next slide, please. One of the papers I wanted to cite has been actually mentioned a couple of times already before, and I really like this paper a lot. Suki mentioned that very clearly several times. The increasing risk of great floods in changing climate. It's a very important paper. So John, if you could move to the next slide, please. So it's a paper because it highlights so many, I think, of the ways that Chris has been contributing to the field. So here's the abstract. You can look at it, but the final line, the recent emergence of a statistically significant positive trend in risk of great floods is consistent with results from the COMET model, and the model suggests that the trend will continue. That's really important. I underlined, though, and read 2 phrases, streamflow measurements and numerical simulations. And this is the combination of observations and models that is at the heart of so much of Chris's work and how he has done, and of course, combining that with theory. So this was a very important work. It actually showed a few concepts really that haven't been shown very much in the literature prior to this. So John, if you could go to the next slide, please. So this is figure 2 from that paper, in which Chris looks at the global distribution of river basins with some criteria, large basins, and also trying to stay away from ones that are heavily modified through human activity. And this is the increase or the change in the risk of 100-year floods in response to quadrupling CO2. So the color codes show how likely a 100-year, what's the return period of a 100-year flood in the future after quadrupling CO2. And the bluish and greenish colors indicate a much increased frequency of floods, and that's very critical for society. But also look at the bottom panel of that caption. The poor performance of the model and low altitude should be kept in mind. And so his observational analysis were applied with rigor to these models to show that actually the models in the tropics weren't doing very well in terms of simulation of great floods. They were doing quite well in the extratropics, maybe due to convective representations versus resolved circulation. I don't know. But it was really important for him to be able to say what the models do well, what they don't do well, and use that as a guide to how to use and how to interpret model results. So if we go to the next slide, please. This is a figure 3 from that paper in which a few very important fundamental points are made. These show the changing frequency of great floods. So on the x-axis is time and the y-axis is frequency of floods. The upper left are the observations. The solid circles, filled in circles, are based on the historical record. So you can see there's a observed upward trend, and he showed very nicely that that is meaningful and significant. The other 5 graphs show an early ensemble. So this is the late 1990s. So ensembles were much smaller then, but a very important message nonetheless. The different panels show results from the 5 different model scenarios, all using the same forcing. The solid filled circles show results just over the historical period. The hollow or unfilled circles show results from the projected period. So you can see a lot of important points. A key comparison of observations and models, forced climate change and natural variability, that really important intersection and trying to untangle those two, changing risk, which can be quantified through these sorts of analyses, and model uncertainty. All these are key themes, I think, that Chris has touched upon in many of his papers, much of his work, and is shown very clearly here in this figure. So if we could go on to the next figure, please. So this is the last figure from that paper, actually, which looks at this increasing risk in a different way. Now plotting, time is still on the x-axis, but the y-axis is a measure of the linear correlation, the trend over time, and they're standardized, so anything above 1 is significant. So you can see that different members, different times, there's a lot of internal variability in the system, but nevertheless a very clear change in risk of the signal of increasing floods. So go to the next slide, please. This is my penultimate slide, please. So I really want to take some time to mention Krista and all the work she has done for us. So again, this is the early on model, and this is on the lower left. This is a measure of the log of river flow in one of our latest models at 25 kilometers. And Krista has just been incredibly valuable to this laboratory in being right at the front of helping in so much the model development. We built a number of models over the years, and I've been involved in many. And one of the first things we always ask is, where's Krista? Because Krista was just absolutely vital and essential to the land component and making sure everything works. So that bottom left panel is a river routing network from our latest model. You can see lots of interesting things. If you could click once again, John, it's not just hard enough to make a model like that. This is actually on the native model grid, which the model now is in a cube sphere. So there's 6 sides of the sphere. And so you have to translate from the lower right panel to the lower left panel. It's very, very complicated. And without Krista, I think it's really a hard case to make that we could do much of what we've done. So big thank you to Krista for over the years, that work. So to go to the final slide, it's just thanks. Thanks so much to Chris for everything you've done over the years. It's just been tremendous for us. To Krista for how much you've helped. It's been so appreciated. And to the USGS for sharing these incredibly valuable people with us over the years. So thanks so much, Chris.
Thanks, Tom. 2 quick points and then another point. Quirky is good. Thank you. In fact, that mirrors my final slide of my talk. Of course, LM4, to get by the time we're at LM4, you know, Lena and Sergey and many others have contributed a lot and really have taken over. But I just wanted to say, and there's lots of smart people at GFDL. They're all smart. There's some high bars to get in, but especially during the creation of CM 2.1, I really enjoyed seeing another aspect of intelligence and just watching your wisdom in keeping that model development going and, you know, herding the cats and all of that kind of thing. So I really appreciate that.
We have a few cats at GFDL. Thank you, Chris.